In the last problem, we assumed that the plank that we were considering, the object of interest, was massless. Because I said we didn't quite know how to incorporate gravity into the problem yet. Well, let's take a look at that. Let's imagine we've got some object, whatever it is, a plank or whatever, and let's imagine that we've got a number of different forces acting on the object that are all parallel to each other. So it's important. Let's imagine that we've got these forces F1, F2, F3, they're all parallel. We can then define a single force. When we're looking at the net force, we know we're going to add all these up, and we could define an equivalent force for all three of them. That's the sum. So we could define a new resultant force, call this F sub r, the resultant force for those three forces, or how many we have, if they're all parallel. If they're all parallel, we can just add up the magnitudes, and we know that the resultant force will be in the same direction, and is just going to have a magnitude that's equal to the sum of the magnitudes of the three forces. If one's in the opposite direction, we'd have to subtract it. Okay, so the components anyways. Okay, well, can we do something similar with the torque? Is it possible to use this resultant force in terms of replacing these three forces? Replace these forces just with a single force to calculate the torque. Well, the question is, where does that torque act? We know for any particular force F1, we have to use the distance x1 that is from the origin. F2 needs x2. F3 needs x3. What distance do we use for our resultant force? Well, we want the torques to be equal. In other words, what's the net torque from these three forces? We have the torque from F1 would be x1 F1. The torque from F2 would be x2 F2. The torque from F3 would be plus x3 F3. And I'm just assuming that theta is 90 degrees in this case, or they'd all have a constant theta anyways. That's the net torque. What I want that to be equal to is the torque due to this resultant force at some other position. Well, that other position would be, let's call it xr for the resultant force. So we can replace all three forces with a single force in terms of the net force, but we can also replace all three forces with a net force in terms of the resultant torque if we apply the force in the correct place at a position xr, such that xr times the resultant force gives us the same as the net torque. Okay, but don't we have to calculate the net torque in order to figure that out? Well, let's look at a very specific example. Let's look at the weight of an object. And we're going to have to assume that the weight of the object, or that the object is close to the Earth's surface. And then we'll see why we have to assume that. Let's imagine we've got some extended object here and an origin over here at some arbitrary point. This object has got some mass, consequently it's got some weight, there's a force acting on it, and we want to try and determine what is the torque that acts on this object due to its weight. Well, the weight is a well-defined force, we can figure out what that is, but where does that weight act? At what point does the weight act to determine the total torque acting on this thing because of the weight? Well, let's think about that. Let's break this whole object down into a whole bunch of little tiny masses, each one with a mass. We'll call them m sub I. So there's m1, m2, m3, m4, m5, up to whatever, some large number of masses. Each one of those has an acceleration acting on it of g, and typically we usually think of g as constant for an entire object, but we could in general say there's going to be some value of gi at different masses. If this is in perhaps a varying gravitational field, we don't worry about that near the surface of the Earth, but in general that could be the case. The total weight, or the weight of each little object, w sub I, will be mi gi. The total weight will then be the sum of all of those little individual weights, or the sum of mi gi. The weight are going to be down, we'll assume. So with a coordinate system like this, if the force is down, the only position that we need to worry about is the one that's perpendicular to the downward direction, which would be the x-coordinate. So at what x-coordinate would we assume, or could we assume, that this weight acts in order to determine the torque? Well, what we would want is, what is the total torque here? Well, the total torque would be the sum of all of the individual torques, all the little tau sub i's, what's the torque on each one, and that would be equal to the sum of r, the distance, now in this case we want the perpendicular distance, which would be x sub I, times the force, which would be mi gi, times the sine of the angle between them, but we've already made that 90 degrees because we're only looking at the x coordinate and the y force, negative y direction. Anyways, so we have sine of 90. Well, there we go. Okay? And what we want is we want that to equal the x position of what we will call the center of gravity. In other words, the center of this thing in terms of gravity, where the gravitational force is acting in order to determine the torque. So x center of gravity times excuse me, the total weight of the whole object. So we want this to be equal to this, the sum of xi mi gi. Now what is the total weight? The total weight we know is the total mass times g. Now let's make the assumption that g is constant over the entire object, so that we can assume that the g that acts on each individual little mass is the same as the g that's acting, we can assume, over the whole thing. So here's where the approximation takes place. If it doesn't, we've got something else that happens. We'll see that later on. But let's assume that all the g's are constant, so that the total weight is the total mass times g. And all of these little g sub i's are the same, just g. So we've got g on the left, g on the right. We can divide off the g. And all we've got are the masses in there. But what is this? This was exactly the way, except we had the m on the other side. We had the m over here, right? This is exactly the way we define the center of the center of mass. So this was exactly the same way as we define the position of the center of mass. What we find here is that as long as the gravitational acceleration g is constant over our object, the center of gravity of the object is exactly the same as the center of mass of our object. Now, what does that mean? It means that in order to determine the torque acting on an object due to its weight, due to gravity, we can assume the entire weight of the object acts at the center of mass of the object. So wherever the center of mass is, we can assume the entire weight acts at that point in order to determine the torque. That is excellent. Let's try and use that.